So, well, let's get started for the evening. All right. Now, I've stopped calling this chapter 4, A, B, C, D, all the way up through J. From now, I want to call it presentation 15, 16, 17. And we're going to take a diversion from just following the license manual. And in here, I've got a list of places to go to follow up on the material, whether you're a technician, general, or extra. So let's get started. Now, here's our chapter 4 review. Ohm's law. We learned about resistance, which equals R, voltage, which is E for electromotive force, or V for voltage, current, which is I. And that I will mess you up if you're a mathematician. So occasionally you'll run into that. And I showed you where that would happen in our previous classes. And we talked about series and parallel circuits also. Now, we talked about phase angle. The current leads the voltage in a capacitor. That's because as soon as you apply voltage to it, it starts conducting immediately. And so the current is ahead of the voltage in a capacitor. And in a inductor, the current lags. That's because as soon as you apply a voltage to the first coil, it radiates out a magnetic field, which causes back EMF. So the coil, which is first getting its current, radiates a magnetic field out, which then in turn stops the current from flowing. And then slowly the voltage or the current increases. So it's the opposite of what a capacitor does. Now, there are two formulas, and these ones everybody really needs to know. The reactance, which is X of a capacitor, C here, is 1 over 2 pi FC. So as you increase the frequency or increase the capacitance, because it's inverted, the resistance goes down. When it's the reactance of an inductor, it's direct. So if you increase the frequency or increase the inductance, then the reactance goes up. I had to stop thinking about it for a second. And then we had impedance, which now remember the rectangular and polar coordinates. The scale that was a cross with R, which was the real one on the horizontal, and then the imaginary, which was vertical. And so you got plus and minus J, plus being inductive and J being capacitive reactance. And you can do that in polar coordinates also, which is you start at 0 and you've got the angle. You start out with the horizontal line being 0, and then you rotate around. You can also do negative angles, but anyway, both of them represent the impedance. You can convert from this to this and from this to this. So, and then we have resonance, which is here. You take a capacitor and an inductor and you hook it up either in series or in parallel, and there's a frequency that they will resonate at. X sub C and X sub L, when they are equal, it is in resonance. So here's the formula. This formula you should know, regardless of whether you're going for technician, general, or extra. This is the frequency of resonance is 1 over 2 pi, the square root of LC. If you have a phone and it has a shoot, my brain just went a calculator on it, a scientific calculator, which almost everyone has, or you can download it easy. These are real easy to figure out. So anyway, here are a series. Here's series, a capacitor, an inductor. They're hooked in series, and this is the well, this is the formula if you want this, but otherwise it's 2 pi LC. And here are the capacitor and the inductor are in parallel. And notice the R's here. Every part has some resistance to it, even if it's really, really tiny. But when they're in series, when you get to resonant frequency, you have the minimum impedance. In other words, it goes down like this. If you're in parallel, that's when at resonant frequency, that's when you get the maximum. If you're looking at the scale, it'll go like this. So, and we mentioned Smith charts. I don't expect you to understand them yet, but later on we will get into Smith charts, and I will show you how to actually solve problems for antennas and feed lines and that sort of thing by the use of a Smith chart. This is a very simplified one. This line across here is the real line. The one is a standard. You could call that 50 ohms, or you could call it 75 ohms, or you could call it 300 ohms. It doesn't matter. If this is 50 ohms, 2 times will be 100, and 1/2 will be 25. And all of these imaginary numbers up here, the plus J's, are inductance, and down here is capacitance. And that's all you need to know about the Smith chart for now, except that someday it's going to be a very nice tool to have. And then we talked about reactive power and power factor. The power factor is the real power over the apparent power. And the power for real is the apparent power. And the apparent power is just simply you get a voltmeter and an ammeter, you measure the voltages, and then you take the power factor and multiply it. You might have a power factor of 80%. You just multiply that times the apparent power, and you come up with the real power of something. So we also talked about Q. And I'm not talking about a Star Trek character. We're talking about electronics here. And I'm going to move this out of the way so we can see this clearly. When you're talking about Q, this dotted line right here is something that has a Q of 10. This line right here is a Q of 100. See how much sharper this is? It's much narrower. And if we come up here to this point right here, the Q of 10 goes from this point to this point, which is a fair amount of frequency spread from here to here. But with the Q of 100, it's just this little tiny amount in here. So that's the delta frequency from this as 1, but that would be the resonant frequency. So if we come back over here, oh, and by the way, this is the -3 dB point. Remember dBs, everybody?
Yes.
Yeah, good, okay. And the formula is delta F, and delta means the change in frequency is from the frequency of resonant divided by Q. And delta F in this formula here is the half power bandwidth. It's the resonant frequency, and Q is the circuit Q. And that's all we need to know about that. Then we talked about skin effect. And skin effect is a really interesting thing. If you have DC and you're running it through a wire, the current runs through the whole wire. But as soon as you start running a AC through it, the current starts moving itself out toward the outer edges of the wire. You weren't here, were you? No. Poor John, he missed out on this. So as the frequency goes up, it gets closer and closer to the outside edge of the wire. If you're working on a 2-meter rig and you're trying to build a power amplifier, you might as well use copper tubing rather than solid wire, because all the current is running on the outside edge. And if you're at 432 megahertz trying to work moon bounce, you better have silver copper tubing for your coil in your transmitter, because all the current's going to be right out there on the surface, and none of it's going to be running inside. Okay, but there is something the AC increases in frequency, Q increases. So if you're going up in AC frequency, the higher you go in AC frequency, the Q continues to increase. So you might go from a Q of 10, in fact, we'll go back, a Q of 10, which is this outside one. As the frequency goes up, it might go to a Q of 100. I'm just making these numbers up, of course, but there's a point where the frequency causes skin effect. The resistance of that wire starts going up. Now stop and think about it. With DC, you've got the whole wire and all the current goes through. As the frequency goes up, the current starts going to the outside of the wire, so the resistance goes up. Are you following that? Good.
Yes.
Now it'll reach a point where the resistance goes up. When the resistance goes up, the Q comes down. So there is a certain point. So here we go. In this area here, you can count on the Q working well. But after you get skin effect kicking in here, you can see what happens with the Q. And eventually it drops off. So anyway, when up to 50 megahertz, probably you don't have to worry much about anything. But when you get in VHF, UHF, it becomes a real critical factor. But actually, I showed you last week the output inductor and capacitor for a Heathkit amplifier. And I showed you the coil that got bigger when we went up to 28 megahertz. Bruce remembers that. Vaguely, yeah, yeah. Yeah, maybe I'll show it to you here again in a little bit.
Good idea.
Okay, all right, well, we will do that. Okay, next. Self-resonance. Here we can see the dotted line capacitance. Here we've got a coil, and it's right next to this coil right here, which is then next to this coil here. Well, there's capacitance between here and here, here and here, and here and here, and also from here down to here, or from here to here, and from here to here. It's all capacitance, and it adds up. And it's as if you have a capacitor in parallel with this. So if you've got a capacitor and an inductor, there is a point where it'll hit resonance, and that's called self-resonance. You do not, if you can see this chart here, it's another of the same thing. If you're using that part in this range here before it gets near self-resonance, it'll work fine. But if you get anywhere in this area here where you got self-resonance, it will mess you up and it won't work correctly. So, and the same thing goes for capacitors, except that the leads of a capacitor are actually an inductor. I've got a little inductor tester. If I take a wire, look at my little picture down here on this. If there's a wire this long, it's an inductor. And if you're working at 2.4 gigahertz, which is a lot of our phone system in our houses and stuff like that, that's a big inductor at that kind of frequency. At 3.5 megahertz, you don't have to worry about it. Okay, this is surface mount components. Remember when I was showing you the resistors and the capacitors, and we have these little tiny parts that look like a speck laying on the screen? Those are surface mount parts. The leads are extremely short. I mean, the end of the capacitor, here I get this in there, you got a little tiny part like that, the end of the capacitor is right there, so there's no leads. And you can, with surface mount components, you can work at higher frequencies much easier. So actually, for those of you who are going for your amateur extra, read that part carefully and study the questions. I do not want to get into that kind of detail in this class. Now, magnetic cores. Has Scott shown up?
Yeah, he's in the room. He just said that he was on a phone call.
Oh, okay. Good. Magnetic cores are something that we need to know and understand, because even if you hardly do anything at all, you'll end up using them. If you put up an HF antenna and you build your own balun, you will be using these little, oh, here, let me get this out of the way. Come on. You'll be using these cores, these toroids, to build your balun. And that's something that most hams should at least try. Give it a shot to build a balun. Actually, Bruce, would you go back and get one of those bags that has the balun kit in it? You know the ones I'm talking about?
Not yet, well, sure.
Yeah, just keep on going all the way to the back. And there's like three, no, now turn right. Right there, there should be 3 in the bag.
3 in a bag?
No, 1 in 3 bags. 1 each in 3 bags.
Oh. Those are Daron's
Just bring
antenna
one.
kits?
And yeah, just bring one, please.
Yeah, Scott built this antenna.
Oh, Scott built this balun?
I believe he did.
Scott, was it a balun or a onion?
Maybe it was an onion.
I don't.
I'm not sure.
I'm not very good at pronouncing these things, so.
His mic,
Anyway.
he may still be on the phone.
Yeah, oh, okay. All right. There are all kinds of cores: air, iron, powdered iron, ferrite, etc. Ferrites have all kinds of mixtures. But here's a coil, and I'll show you some samples of this here in just a little bit. But this is an air core. And with an air core, if you running RF through this, it sends out magnetic fields that just go like this. They just radiate out forever. And then we've got these guys. These are iron core. Oops. These are iron core transformers. They usually work at like 60 cycles AC or 50 cycles if you're in Japan or Europe. But they're big and they're heavy. And this core, and we're going to talk about saturation, that's why they're laminated. So you got a primary, here's a primary winding, and here's a secondary winding. And Scott talked about disassembling those when he was young and rewinding them for his purposes. And that's a common thing to do. You could take this, and if it had 12.6 winding on it, you needed 6.3, you just rewind it. And this was a common thing done in the 50s, 60s, and 70s. I know that I wanted to do these in that period of time also. So anyway, that's an iron core. Now here's a ferrite core. This little guy right here has this coil right here, but up the center of it is a hunk of ferrite, and it has a slot in it. Many of them are just like a six-sided hole, and you've got little tool you can stick in there, and it's threaded, and you can screw the ferrite in and out and change the inductance of this. So, and then we have toroids, which are these guys here. And these are nice because the magnetic field of these pretty much stays inside the center of the coil. And so you can place these parts fairly close to each other and they won't interfere with you. But if you took one of these and had another one sitting over here, this would radiate into that. And if you didn't want them to interact, you'd be having trouble.
You'd have to build a box around it.
Yes. Hi, Scott. Welcome back.
Thank you.
Bruce, go ahead.
Could you build a wall between two of those air coils?
Yes.
Okay.
Actually, that's what you do. They just
That's all right. No
they
worries.
make little metal shields that separate these things. In some of the radios tonight, I may be able to show you that. So now one of the this here. Oh, and I should have done this large. This here is a toroid. See this wire going through here? This one wire running through the center of this toroid is considered one turn. This next one over here, you can see the wire going in here, then wrapping around and going through it second time. That's 2 turns. And that's something you need to understand, because if you have this kind of transformer, this is 1 turn up here. But down here, this is 1 turn. And you need to remember that if you ever work on these. So we'll be showing you more of this stuff later. One of the things that you want to avoid is saturation. What is that?
Something from Fred. Thank you.
Oh, Fred, can you mute yourself, please? These cores are, if you look at this one, here's an E on the bottom with a bar on the top. Here's an E on the top with the bar on the bottom. Excuse me just a second. The iron core the iron transformer core is laminated to keep down eddy currents. Woo! I was trying to remember that from heart and I couldn't remember it. What happens is the magnetic field that's in this core will cause currents in the coil. But if you laminate these and keep the each section physically separated from the others. In other words, each one of these cores has a coating on it so that they're not done. It'll cut down on the eddy currents, which you would be wasting a significant amount of power in the core if you had the eddy currents and wasting power, and it would not work as efficiently. So that's why they laminate it the way that they do. Okay, and the one thing you want to avoid is saturation. Each of these cores will saturate if too strong a magnetic field is put into it. That's why if you're using these things to for a balun for your antenna, which is likely something you will do or use, if this core is good for 100 watts and you try to run 1500 watts through it, that'll saturate the core. And then when you saturate it, it will not give you a pure AC or a pure sine wave in and out. So you need to size the core or stack the cores so that you can handle the magnetic field. Yes.
Remind.
Anyway, the most efficient shape is the toroidal shape. These here. So, and then beads. Beads are little tiny toroids. And if you ever see them, you might have a transistor soldered into a soldering board, and one of the leads will have a little tiny bead on it. What that does is keep that transistor from going into self-oscillation. And if you see one, you'll know what it's for. If you're having oscillating problems and something you're trying to build, that's a good thing to try. So now moving on, I want to start tonight, and I'm going to talk about our basic equipment. I mean, the reason for amateur radio and the tool that we use to do anything we want is a radio, right?
Yeah.
I mean, we use radios to transmit signals out over the air. Doesn't matter if you're trying to talk to Hong Kong or to the guy across the street, whether you're doing emergency traffic or you're just shooting the breeze, having fun. That doesn't matter. But every one of us, we use a radio. And there's all kinds of radios. And for my technician friends, your very first radio will be a VHF radio. And it operates at about 100 and I'll say 45, 48 megahertz. And that's a high frequency. And the wavelength for that is 2 meters. So 2 meters, that didn't show up on the screen. Half of that, here, now wait a minute, let's see. There we go. Well, that's less than 2 meters. Anyway, 1 meter is the length of an antenna. Full dipole, or a quarter wave for a vertical antenna, which is about 19 inches. So that's a high frequency. It's a short wavelength. And for your local communications, that's what most of everybody will be using for emergencies, are VHF radios. They'll be either operating simplex, that is radio to radio, or through repeaters, which is there's a radio sitting up on a hill, and you have your handheld. You have your handheld. Try to figure out how to do this looking at myself on your handheld. Actually, this is John's handheld. I'll show you mine in a little bit, but anyway, you can talk radio to radio, or you can talk to the repeater that's up on top of a mountain, which will give you much greater range. But VHF and UHF, it's a straight line of sight. When the signal goes out, it goes straight. If it runs into anything, it quits. If it goes into the air, it goes straight out into space. It does not bend or reflect or do anything. So if you can see it, very often you can talk to it. I remember living west of Portland, up on the hill, and I could see Mount Hood, and I could talk to the Mount Hood repeater, which was a long ways off. But I could see it. So it was a line of sight. So, and then we have HF radios, high frequency radios that work from 1.8 megahertz up to nearly 30 megahertz. And many of those actually will also work at the low end of VHF, which is 50 megahertz. That's 6 meters. So we have all those bands, 160, 80, 40, 30. Yeah, well, I was going to skip the ones in between, but you're right. You're right. 30 meters. And that's kind of interesting. I'm an old ham, and I just somehow I can't get used to all these new frequencies. When I was at first a ham, the frequencies I'm telling you now were the ones that they had. So anyway, you got 40 meters, 20 meters, 15 meters, and 10 meters. And then you got 6 meters, which is 50 megahertz, and goes up from there. But the HF are intended for distance communications. You can, by using a low antenna, which is called an NVIS, which will help you keep the signals close to you, and that'll give you a range in up to about 600 miles or so. So, and then then you get into the digital. And amateur radio today is just full of digital communications. There are things on VHF which allow you to not only does it take your audio, turns it into a digital form and transmit as digital. That digital communications also very often can be hooked to a repeater and go out over the internet. And you can literally, with your handheld radio, talk to somebody in
Australia.
well, Astoria is close. I'm talking about
You said Australia.
Australia. Yeah, there we go. My mind's going blank. I'm trying to think of all these exotic places that I can, or Hong Kong, or Moscow, or London, or because it goes to the repeater, which is local, and the repeater is hooked to the internet, which goes all over the world. So that's one form of digital. And you can do digital on HF also. We have emergency communications which operate, and now I'm going to fail on remembering the name of it, but there is a system where you can send messages via HF. It's slow, but you can hook up to another radio, and when you're using this form of communications, you have a program on your radio that goes over the HF frequency and hooks up to a radio in another location.
PSK 31.
What?
Are
Oh,
you
no,
thinking about PSK 31?
no, I'm talking about the one they use for sending email.
Oh, WinLink.
WinLink, that's it. Thanks, Scott. Scott,
Yep.
say me again. Yeah, WinLink can do that. And so you can, I'll just talk about emergency communications. Let's just say the big one hit here off the Oregon coast. That earthquake would result in a tsunami. Most everything, because it's going to be a huge quake. It's going to be an 8. When it goes, everything will be devastated. It'll knock down buildings, it'll knock down towers, our repeaters will be gone, our communications will be gone, our power will be gone. I mean, that is a real scenario. It's not a maybe. Someday that's going to happen. I hope it doesn't happen in my lifetime or any of my friends or my great grandkids' lifetime, but it's going to happen. And when it does, it's going to devastate this coast. And we'll have no way to get out other than by satellite or HF radio or VHF. And with WinLink, we can send out email messages. We can send it to our Janet and my kids that are in Arizona or on the East Coast and say we're okay, we're alive. You know, we can send information via that with pictures even to the state to let them know what's happening over here on the coast. I mean, there's all kinds of things we can do. And a lot of people just do this stuff for fun. I mean, I think some of the things you can do is television. Speaking about sending pictures, you can over HF send a picture. And it's slow, but you can do it. If anybody remembers the old modem radios, computers, you'd dial it up and it'd go, drive you nuts. And then pretty soon a picture would come up on your computer. Anyway, it works, but it's slow. There's specialized equipment for EME. EME stands for Earth, Moon, Earth. That's literally transmitting a signal, bouncing it off the moon, having it come back all the way to the Earth, somebody receiving it and somebody answering it. And you can literally do that with 100 watts now with digital programming. So it's pretty amazing. And then there's contesting. Some people just love to have a contest. And a contest comes on, they get on the radio and they start talking, they start calling CQ contest. And somebody answers them and they see how many people they can work in 24 hours. You know, some people do it just for fun. Some people get really serious about it. I kind of enjoy contesting. That's because I don't like getting out and talking to somebody that I don't know. I can do without that. But a lot of people just love it. Scott's one, you love to just get on and talk to somebody, right?
Sure do. They call it rag chewing.
Yeah, rag chewing.
Rag.
Exactly. In fact, they used to give out a rag chewing prize of some kind. I can't remember what it was. I've never earned it. Anyway, those are the kinds of things that we can do with radios. So now let's take a look at some radios. First, I'm going to show you this radio. I'll get this one out of the way. This is John's radio. What have you got here, John?
That's an 8-watt Baofeng VHF UHF radio.
Can you tell us any more about it? How much did it cost?
Oh, I suppose with that aftermarket antenna, I might have paid $50. That particular radio right there has a larger battery. If you were to, the radio's off now. If you push the clip on the back of the radio, you can take the battery off. It's at the top there above the strap. There's a little clip there. Yeah, just push that and now you can hold into it, pull the battery off. You can see that that battery is much larger than the radio. The actual battery that comes with it is the size of that back plate on the radio. So
just this portion right here.
correct. Yeah. So and it's 8-watt. Baofeng sells mostly 5-watt radios.
That's a lot of power for
So
a handheld.
it's a little stronger. And like I say, it's VHF and UHF. It'll hold 128 channels or frequencies.
Yeah. Yeah, well, this is a very inexpensive radio, and here on the coast, they perform actually fairly well. We don't have the intermod problem that we have in the big cities. So that's one radio.
Oh,
It's, yeah,
Joe,
Yes, go ahead.
I was going to say, while you're mentioning that radio, that was my main radio for the first 10 years when I got my license again. Um, and I still have those radios. I have one that I put in each one of the cars. And I got one
Yeah,
that I can use at home, and I can hook it to a little amplifier and put out 40 watts that way very easily. But at any rate, so very, very expensive. I'm using the same rechargeable batteries that I got with the radio. Um,
how
now,
many years?
13 years now, excuse me, 10 years now. Let's see, I guess,
They have
yeah.
nickel metal hydride, right?
I'm not sure what they
Yeah.
are,
yeah, turn it over and take a look at it.
but so the same, a very low maintenance radio. You can change the antenna to some other type of antenna if you like for a little more range,
Yeah,
or
like
a
this.
stubby antenna for less range and a little more easy to handle.
Actually, this is a lithium ion battery.
Yes.
Yeah, they've come a long ways. The old NiCad batteries had their limitations. But lithium ion, nickel metal hydride, those are very, very good batteries. But
It's got
go ahead.
it's got good audio, and it's an extremely nice radio, and especially if you buy the Baofeng B-Tech radio, because that is certified for use in the United States by the FCC.
Hmm.
And that's why they're a little more expensive, the B-Tech, but another $20, and
You
it's a
want
wonderful
to
radio.
explain about the other ones, Scott? The non-certified?
Well, the non-certified, it's a wonderful radio, and it covers a lot of territory, you might say, from 150 some.
That really isn't what I meant, Scott.
Oh, okay.
An uncertified radio by the FCC is not legal
Right.
because it has not been approved by the FCC. And a lot of people have tried to sell them in the United States, and a lot of people have bought them. I don't recommend that you do that, but you should ensure that they're certified by the FCC. Because if they're
That's what happens. That's what happens when you get, instead of a regular Baofeng radio, you get the B-Tech version of that.
yeah.
Yeah.
Can I ask a question? This is Bill. So that radio you're showing, can that be hooked up to like a mag mount antenna?
Yes.
Oh, yeah.
Yeah. You can unscrew that. Joe, you can show them how to unscrew that antenna. Now you can hook a mag mount right to that.
Yeah,
Okay.
there's the connector. This is a reverse SMA from what we're used to. We usually have this section here on the radio.
Uh-huh.
So this works the other way around, but you can either use an adapter or you get an antenna with that kind of connector on it and put a mag mount on top of your car, and it greatly extends the range of the radio.
Yep. And that's why I say, the ones that I've got, I use them in the car, and I hook them with a little conversion connector. I hook them right to the mag mount.
Yep, and somebody mentioned using an amplifier. If
Yep, yep,
you can get a little amplifier that'll take the 5 watts and turn it into, say, 30 or maybe even 50 watts, which is quite a bit of power. And so you greatly extend the range of the radio doing that. By the way, this radio, you can talk to satellites with this radio.
yep.
So you can get on and the satellite go by, you can talk to it. And I showed you earlier in the course us with Daron talking to somebody nearly on the East Coast through a satellite with a handheld just like this and hooked up to an antenna. I was holding the antenna and it was kind of heavy. And I about wore myself out, but I kept pointing it at the
I
satellite.
think I was in Virginia.
Yeah, I think that's right.
Yeah.
Yeah. So I mean, you can do amazing things, really, really fun stuff. So anyway, I'm kind of a funny person. If I do something, if I do it once, well, I've done it now. Now I'm not interested anymore. But Daron has talked on to the International Space Station many times. So now here is my Go Pack, which you can see. I mean, I can hold it in my hand. Here it is, and then I open it up, and here's my handheld radio. I set this on the floor. Now in this bag, by the way, in this there's antennas, connectors, extra batteries, all kinds of stuff. So here's the radio. This is a 5-watt radio. It's 3 bands. It works on 2 meters, 1.25 meters, which is 220 megahertz, and 70 centimeters, which is 432 megahertz. So this works on 3 different bands. I have talked to satellites using this radio. And I leave it in my Suburban. I have a plug here on the side. This plug, I hook up to the 12-volt DC, and it's always charged. So this radio, it's great, and just this little tiny thing, and you can do so much with it. And this is, Scott was talking about the little stubby antennas. Here's a little stubby antenna, and this antenna works on 3 different bands.
And can you unscrew that and put a connector on it so you can hook that to your mag mount if you want?
Yeah, see, there is the reverse of what was on this radio. That's the actually that's the female. The tip, I don't know if you can see in there, if you can see the tip that's inside this right here. That tip is what makes it male. And this here, you can see the little hole that the tip goes into. That's what makes it female. So this is the female connector. Then whatever is going on the outside doesn't count.
So for Joe's radio, he uses he's got a female connection on the radio, so he gets a little adapter that's got a male tip on it so that he can put that on there and then hook it to the mag mount antenna, and you get just the opposite kind of connector for the Baofeng.
Correct. You just when you have your radio, you got to find out what kind of connectors on it.
Yep.
And make sure you either have this right connector on your antenna or an adapter to adapt it. So anyway, I want to show you. How much time have we got, John?
Let's see, we have 6 minutes.
Okay. Here's my kit. By the way, some people, let's see if we can get this to focus.
It's a little,
Yes.
it's a little too much light, maybe.
Yeah, there.
Yeah, that's better.
Yeah. This is turn on volume. AB receiver, VFO memory selection. This is my cheat sheet that I made at a club meeting one time. In fact, we all sat down and we made our own cheat sheets. So we knew by hand what to do in order to get it to set. And here's a picture of the this radio here. It's a TH. You can see right there, it's a THF6 by Kenwood. This is the radio, and here are the various things I pointed at. So I made this up by hand so that if I am in a position where I have to set the radio up at a different frequency and different repeater, I've got the information right here. And then I have this antenna, which I'm going to have to go like this to show you the entire length of the antenna. But this makes it a long antenna. It's much more efficient. Let's see, what else have we got in here? There are these. Let's see. Nifty quick reference. This tells you briefly how to set up and work the radio. These are available. You can purchase them. This is for those especially who would like to do emergency communications. Here I put a little card in here. If found, call 00. Oh, I gotta change this phone number. I got rid of that phone number 3 years ago. Oops.
Gotta keep it up to date, Joe.
Oh, yeah. So anyway, and then, well, let's see what's in here. These are just things that, and you can see how small a package it is. Oh, here are adapters. Yeah, let's pull it all out. I'll have to, oh boy, oh good. I forgot I had this. Okay, here's a power plug. This will plug into any car. This plugs into the radio and it'll charge it. Here is an SMA male to a BNC, not a BNC, excuse me, to a PL259 adapter. And here is,
Joe,
yeah,
Joe, would you let them know that the PL259 is what it hooks to the mag mount antenna, and the SMA hooks to the little radio?
oh, yes, this part hooks to my radio. Fact. There's the SMA male, just screws on here. I'm just going to go do that part. And then this will hook up to many antennas out there that fit the PL259. And that's an SO239, which mates with this. And then there's this, and here again is the SMA connector, which I'm trying to be in too big a hurry. It screws on there. I won't do it all the way. And this is a BNC connector, which is a common kind of connector that is dated now, but boy, I'll tell you, they're good connectors. So anyway, all right. And let's see, what else have I got in here? Oh, here's a SMA male to a PL259. What else have we got in? What is this? Oh, here's SMA, female to SMA female adapter. And then oh, okay. Well, this is exciting. I haven't had this stuff out in ages. Let's see what else we got here. That's it.
Oh, and all those connectors, pretty much, you can get off of Amazon. As
They're not very expensive.
and also the mag mounts, and they're very, very inexpensive.
Yeah, boy, I haven't had this out for quite a while. It is a tangled. Whoops. I need to get this over here so you can see me fumbling around. So there we go. Wow, boy, I tell you, it's a good thing I didn't have an emergency. There, I think I've got it untangled finally. Here's the earpiece.
Microphone switch.
Here's the microphone switch here. This must be the microphone. You think that's what that is, Scott? I don't know. It's like,
Yep, that's what that
this
is.
the switch. And then this plugs into the side of the radio, which goes just like that.
Then also, you got probably that same thing that hooks up. You can get a little cable that hooks to that hooks to your computer to where you can program it using your computer at home if you want to.
Yes, Scott.
And that's with
Actually, Scott, it's time for our break.
Yep.
And we have a cable here that was provided by David Davis for hooking up to a computer. And it must have 8 different plugs on it. I'll show it to you following the break. So let's take a break and we will be back in 10 minutes. So hang in there, everybody. All right. This is the snake that David Davis gave to us. Now look at this. I tried to put my my radio away and I left this bag, which has this very important thing, my spare battery. I should charge this up.
Uh-huh.
Yep.
Sure.
Probably. The things to remember. What's the name of the program that we use with
Chirp.
Chirp?
Chirp.
Chirp is a program. You've seen Daron here. Daron is a friend with the guy who developed Chirp, and he lives in the Portland area. I've met him and his wife. They're both really wonderful people. But with a USB connection to your computer, and here's the USB connection, which is this cable right here. Generally, in the past, if you wanted to hook up your radio, you would have to buy a USB connector with an adapter with one connector on it. But somebody has figured out how to wire up all these different connectors. So whatever cool. Man, it is cool. David brought a computer over and he left it. He had a note on it. He says, this thing's set up only to do Chirp. And here was this package, this thing, sitting on top of it. And I just couldn't believe it. I mean, I've got at least this many of these at home, which I should bring here and leave them here so that they can be used by everybody. And each one, they're expensive. I don't know, what are they, $30 a piece or something
Maybe
like
not
that?
that much.
I don't know, $20. I mean, you spend it.
Yeah.
Well, here they all are in one device. So if you
Oh.
need to program your I started to say computer, radio. There's a computer all set up with this cable.
Oh, Joe,
Yes.
let them know though that you don't need all those connectors. For instance, that little radio you've got sitting there, you pick the connector out that you use for that particular radio.
Well, right. Yeah, you just use one. And I'm not sure, Mike,
It's the one with the two connectors, kind of like yours. But
On the right-hand side,
yeah, but that one's handy. The multiple one is handy for somebody who, like at the club, who may want to help a bunch of different people with different radios program their radios.
yeah, there you go. I had it out of, sorry, folks. But there's the connector. And it just plugs in like that. You might have a mobile radio instead of a handheld with that kind of a plug. I mean, there's all kinds. Here's one similar to the one we used before, but anyway. Correct, Scott. Well, let's move on. Let's go to HF. And if you allow me, I'm just going to set these things over here.
Oh, thank you. I just got through dinner. Appreciate it, Bill.
I need to
John,
change my
very
phone
kind, yeah.
number. Okay. Now we can go to HF, but before we do, this is for Bruce.
For me,
Yeah, now you remember
yeah. We talked about that.
we talked about this radio before,
True.
and you asked why they didn't just start with low frequency here and go up to the high
Exactly,
frequency,
yes.
and why that is. So by a little bit of investigation and inspiring, you see this connector right here?
Mhm.
It goes to these wires, which are right underneath here, that come over here and operate each one of these relays.
Okay.
Now, they could have wired those any way they wanted to. So why didn't they just go from low frequency to high frequency, or vice versa, whichever one it is? But they did not. This one is 28 megahertz. This one is either 80 meters or 160 meters. I'm not sure which. But see, this is the highest frequency and this is the lowest frequency, because we can tell by the number of turns on this coil.
I get that.
Remember I said that these can interfere with each other a little bit?
Yeah.
I think that they've spaced them out like this to keep them from interfering with each other. I think they're using that as their method of isolation.
Okay.
Now,
It doesn't explain why, like, starting one going to the other end, though.
well, by doing this, they keep the bands from interfering with each other.
But you still do A, B, C, D, could you not?
No,
No,
it's more like A, C, D, F, B. They're out of order because if the frequencies are or the bands are too close to one another, right next door to each other, the 20 is right next door to 40, then it interferes more than if 20 was next to 80.
I got you. Okay, thank you. Appreciate that clear up.
Okay, now, remember we were talking about isolation? Now, I believe this is probably the IF strip right here. That's just a quick guess. But see this metal frame here? That creates isolation to keep it from interfering with stuff over here. Here's another transformer, and here's a shield. Here are some more transformers, and here's a shield. That keeps these from interfering with each other.
Now, would that shield be just an aluminum box?
I
Yeah.
think go ahead, Scott.
I was just gonna say, yeah, sure. Or copper.
Okay.
Well, I am not certain, but I think there's a possibility it's tin steel.
Yep.
I do not know for sure.
Okay, I'm just curious.
Here's something that, see this strap here?
Yep.
That's so that this will apply the ground, which is on this case. Here's a whole thing that's completely closed off. And this grounds it to the bottom cover for the radio. So they're connecting this ground to keep it from radiating.
Huh.
Got that?
Got that.
Good. Yeah, okay. Now here's a radio. This is a 2-meter radio. It works at 145 megahertz. Here's the front of it. I'm a little too close. 231. This is a 2-meter radio. There's a volume, there's a squelch. And you can change the megahertz and so on and so forth. But inside this guy, we have several things. Notice we talked about shielded area. Here's a shielded area to shield the radiation from getting in. This module right here is the power amplifier of this radio. Notice these little guys right here. Those are variable capacitors for adjusting. See the coils? We got several coils in here. And then we've got, remember I talked about being able to adjust these coils. Here's the core, and that's a little rectangular hole. And they got a tool that slips right down in there. I wonder if I got one of my tools handy. Okay. Oh, yes, here we go. Here's the tool. Let me get it over something dark. You can see here on the end of it, there are two different sizes. And down here is a shorter one, but there's two different sizes of hexagon connections. And all we do, see it's the smaller size, we slip it in there, and then we can twist this back and forth to adjust it, which I don't want to do. Although this radio is dead, this output module is bad. By the way, this black plastic thing is just a black plastic cover that goes over this whole thing, which is metal with ceramic on it with the amplifiers built on that. And with this particular radio in the next generation of this one, what happens with these modules, the ceramic would crack from getting hot and cold. And then it quit working. And some of them you can actually repair by removing this and then putting a solder bridge across where it cracked. So anyway, here's the power that comes in. Here And these are little electrolytic capacitors. These guys right here. And well, here's a crystal, which is used for an oscillator. It makes a very, very stable frequency. And then we turn this over. And I want you to see that. Now I'm going to actually get this much closer. Ta-da.
Wow.
Yeah, Joe, don't move.
Now, those are put together by a factory, they're not individually built by an individual.
Yes, what happens, there's a machine
Solder rack.
that they have one that covers all these spots with solder. It's a solder paste. And then they have another machine that comes along and it installs each one of these parts. It just sets it there.
Okay.
And they're held in by tension. And then they run it through a heater, which actually heats this hot enough to melt the solder, and each one of these connections are made.
I just wonder how you would avoid the solder bridges that are traditional with soldering things that close together.
They put just enough solder to do it, and when it gets heat, you can watch it. If this part is put in, it's a little bit crooked, it will just wiggle back and forth and line itself up. And that's what they do.
Wow.
So it's amazing to watch. This is a resistor. Now look at the size of my pen tip. That's a resistor there. There's the resistor there. Okay. Here's a capacitor. That's a capacitor there. That's a capacitor. See it? See how the capacitors look? Now here's another resistor.
Is that numbers? Those are values for the resistor on there?
Yes, those are values. The capacitors they don't show. But the resistors they do. Here, well, here's a 100K resistor right here. So let's see what else. Here's another resistor over here. That looks like that's a transistor. That's a power transistor right there. And here are more resistors. You can see that 778. And I can't see it. 472. That's 4700. 4,700 ohms. That little resistor right there. So you can. This is modern construction. Although this radio is pretty old, this is pretty much what they look like today. And they use these little tiny parts. And this is an integrated circuit that probably has thousands of functions, literally. So anyway, let's see what else I can show you. Now get this guy out of the way. Now I previously disassembled this. So I've already got the shield inside that goes over the transmit portion. And I have this, the top cover off. Now what you're looking at, I got to find a place for this. This is an HF radio. This part is the amplifier. And it's got this huge heat sink to dissipate the heat that's generated when you transmit. And then here's the speaker right here built into that. Now we just simply pull this off, and I disconnected everything earlier. And here we go. Here, well, let me turn it around this way. Here we go. These are the interconnect cables. Now, I have had this particular style of radio apart many times. But before I disassemble something, I take my telephone camera and I photograph everything so that I can figure out where it goes when I want to put it back together again. But somebody want to tell me what this is? Does it look familiar?
It looks like toroids.
Yeah, this is the same thing I showed you in the other. It's either a bandpass filter or it's a low pass filter. I'm not sure which one for sure this is, but I also want you to notice, see that coil there? That one's probably, because that's the smallest coil, that's probably 10 meters. And so this is a smaller toroid, but that's a bigger one. You notice spacings are about the same, but they're each going to work on a different frequency. And then down here, we're probably got, I don't know if this works on 160, it works on 80, but so just by looking at it, $160, $80, I'm just guessing, 40, 20, 15, and 10.
So there'd be no 30 on that particular.
No, this is too old a radio for that. When I'm going to show you, I got to get these guys out of the way. I'm going to show you a brand new radio in a little bit. I've got it on my computer. I don't have it here, but it's an Icon 7300. It's a current radio. It's a very popular radio. It's all computer operated. You have one?
Yes.
I'm going to show you the inside of it. And you want to know something? It looks about just like this. For this section of the radio. This is the transmit side. Well, actually, this side is used for receive and transmit. And you select each one of the bands. And there's details I'm not going to get into right now, but you need to be able to do that. This is the transmitter section. I want to switch cameras again. Okay, now we can get a close look. Here's the transmitter section. And if we start at this end, there's a transistor right here and right here. These two transistors drive this transformer. This is a transformer right here. It's similar to the toroid. Oh, here, wait a minute. It is similar to this toroid, except that it has two sections like this. This is the output toroid. These are the output transistors, these two, they're in push-pull. And then this is the driver that's driven by these two transistors, most likely. And then this coil that's here is what drives these two transistors here. So this is a toroidal coil, but it's a different shape than what we normally think of. as this. So we actually have here, this is the RF input, comes from the other part of the radio. There's an amplifier, it comes in, there's a driving coil here, drives these two transistors, that and then goes through this transformer that drives these two transistors. Now it's hard to see, but you can see elements down here where they're connected to the board. And by the way, this little device here is a heat. That's cute. That's a heat sensor. And this right here is a heat sensor. So if these transistors overheat, this will sense it and shut down the radio. Which is a good thing because these things, if they start heating, they can go into what's called thermal runaway. And the heat causes it to draw more current, which then in turn causes it to draw more current. And they burn themselves up. So in case that happens, you have these little devices. And I think just about every amplifier I've seen have those built in.
Now, say it did go over in an overheat situation and it shuts down, will it also come back on when it cools down?
Yes.
Or do you have to reset it?
No, it'll just come back on.
Thank you.
So anyway, this is quite an old radio. But what's amazing is that the new radios look essentially just like it. So this is this transformer right here. This is the output, and you can this is working well. You can see there's about there's 3 turns. Actually, 1, 2, 3, 4. 4 turns through this, and it's double. And so this is the output right here. And you can see that it's connected to this coax, which then goes over here and feeds the filter section, which is probably a low pass filter for each band. But what happens is an amplifier can generate secondary signals that will go out to the antenna if you don't have something like this to filter it. So that on transmits, you want the filter to keep from sending out unwanted signal. And on receive, what you want to do is keep unwanted signals out of the radio, which will interfere with how it works. And then, of course, here's a fan, which blows across everything. Oops, excuse me.
Oh.
This fan here that keeps it cool. These transistors here are physically mounted to this heat sink. And when the fan blows, it blows airs across it. Across this big, huge heat sink. And that's what keeps the radio cool. Remember Ohm's law? A fair amount of what we're doing here is through a resistive load. The transistors are partly resisting. I mean, yes, partly resisting, and they generate a fair amount of heat. So, moving, let's see, it's 8:12. Did I have some other, I had some other goodies to show you. That's one radio. Okay. Oh, yes. Okay. This is the same radio. And let me transfer. Sorry about the. There we go. Okay. Here is one circuit board on this side. And if we remove the bottom, here's the other side. And y'all, this is recognize this, Bruce?
I sure do.
Yeah, well, this is one of several IC 735s that I've worked on. And I like these little radios, and I've got one of these in my Suburban. But anyway, fun things. Maybe I should tell you something about the front panel first.
Go for it.
Power switch. Okay, here's the volume control, and this is the squelch. You might remember that from your handheld radio. My recommendation is when you're working HF, you don't turn on the squelch. But some people like to do that. Here's the microphone input. These are for headphones, 1/4 inch, and you put your headphones on and listen. And then we have the various modes. Single sideband. We've seen that on the oscilloscope. If you're not talking, nothing, no RF goes out at all. You start talking, it puts out RF. CW, that's continuous wave. That's you use a key, you go da 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 da, so on and so forth, you know, for CW. Here's AM, amplitude modulation. Now, this is a 100-watt radio. An AM, it only puts out 25 watts. That's because it puts out constantly 100%. So with amplitude, when you amplitude modulate it, the peaks go up from the carrier higher. So you can't, the radio will not handle the extra voltage. So you have to lower the AM. And then this is FM, which is probably the toughest mode because it puts out a constant carrier and you change the frequency rather than the amplitude of the signal to get your talking across. Let's see, I need to, there we go. Noise blanker, that's for noise like the spark from your car, that kind of noise. That's an attenuator. This is a preamp. This amplifies the signal as it's coming in. This is the automatic gain control for receiving signals. The radio, the atmosphere will cause the volume to go up, down, up, down, up, down. And what this does is it just automatically adjusts the volume. And this is the compressor, which Scott, did I just call that the right thing? Earth to Scott? Maybe he's given up on us.
It's probably muted.
Okay, well, anyway.
What does it say on the button?
COMP.
Compression.
Yeah, compression.
Oh, compression. That helps your audio to have more impact. So that if you're trying to work somebody, rather than just having a normal sounding voice, it emphasizes it so it'll help punch through. So
Kind of like a volume control type thing.
no, it actually changes the frequency of your voice.
It does.
Yeah. Yeah, it emphasizes the high, I think it emphasizes the high frequencies so that you get a little more punch through. So that the power is in the high frequencies rather than the low frequency.
Okay. Thank you.
Okay. And then the noise blank level, RF gain, RF power. This is Vox. Vox is voice operated transmit. So if you got the Vox on and you just speak into the microphone, it'll switch automatically to transmit. And then the microphone gain is the gain for your microphone. So you can set the right audio level. And these are for keying. These are for the filters. And here's the ALC is the automatic level control. That's used on transmit so that you don't over modulate your transmitter, which will cause it to create all kinds of spurious signals, which is not a good thing. Of course, the main tuning knob. And then we have over here, now this particular radio, shoot, here. I'm having trouble getting it. It's too bright. But these buttons change the frequency tuning. This is kilohertz, megahertz, amateur radio, and this is scan. Here we go, VFO. That's VFO-A or VFO-B. This causes VFO-A to equal VFO-B or vice versa. Yes, that way. And then this is split, which allows you to receive on one frequency and transmit on another. When you're working contests or you're trying to work DX, when you're working DX, the guy in the other country may be able to work on a frequency that you can't. So he will work just below our frequencies, and then you can try to call, then you will call him from our frequencies. So that's called split operation. Receiver increment tuning. By changing this, you change the receive frequency, but you do not change the transmit frequency. And there's RIT, receiver increment tuning. If you press that in, it makes this work. With this out, your receive and transmit frequencies are identical.
Just above that, you got a, sorry,
Go ahead.
just above that, you got a notch, and how accurate is the notch side of that?
The notch is an extremely sharp filter.
Yeah.
Yeah. And so if you've got a tone that's on the frequency you're trying to do, you can take the notch, which is this button here, and you can tune it back and forth, and you can actually eliminate that one frequency that's coming through.
Huh.
It's usually it'll be a single tone, or it might be CW, but by doing that, you can eliminate that, and that makes the person much more understanding. So moving on. Memory, there are memories on this. I don't know. This takes the memory and puts it in VFO. And these are your channel up downs for the memory. But I never use a memory on HF. So anyway, back to here.
Oh, may I?
Yes.
I just wanted to let folks know, especially the newer folks, that all those buttons and so on that are on there, that Joe just really did a great job of going through to give you an explanation on them.
Yeah. What do you want, Scott?
You really only need about 4 of those buttons or controls initially. All right, and then you learn how to use all the other ones as time goes by. Right, Joe?
Absolutely right. Thank you, Scott, for for bringing that up. Yes, definitely. Yeah, you actually you need your microphone with a push to talk button on it. The frequency you're going to operate and the mode that you're going to operate, probably single sideband. Probably not CW for quite a while till you learn how to do that. But anyway, yes, That is correct, but all those things are available in amateur radio, HF rigs. So we are going to be getting into operating these radios and learning. We're going to learn what all these parts do and how they work. So, I mean, here, for instance, is something. Here's the single sideband filter. What this does is allow probably about a 2.7 kilohertz signal bandwidth to go through. And then here's a CW filter, and normally they're about 500 hertz. So you can eliminate a lot of CW. And by the way, the narrower your filter, the better your signal to noise ratio. So you can get a lot weaker signals if you have a CW filter. This one does not. Here are 3 trimmer capacitors. Here's a transformer or a coil with an adjuster. That one has, you can see down inside there's a little slot. Here are capacitors. See these capacitors here? Those are disc capacitors. These green things are resistors. Here's a crystal and here's a crystal. These with transistors and stuff, they oscillate. And what's nice about these crystals is they lock you to a very specific frequency. So let's get away from this for a minute. Okay. Next week, these are the things we're going to be talking about: transmitters, oscillators, modulators, drivers, amplifiers. On receivers, we're going to talk about RF amps, mixers, the intermediate frequency. And very briefly, if you have a mixer and you have your radio signal coming in, and then you mix it with another frequency, you will come out with an intermediate frequency. And the intermediate frequency does all the amplifying. So that's why you have IFs. But we will get into that. We have demodulators that take however form it is. If it's AM, it turns it into audio. If it's FM, it turns it into audio. If it's single sideband, it turns it into audio. Now, this we will get into, but for right now, I want to get this down here out of the way. Here is an antenna. This is the diagram on how my 10-tech radio that I've used for this class in the past works. So here's the receive side, goes through a low pass filter, band pass filter, an RF amp, comes down here to a crystal filter, down here to an IF amp. Here's another, this is another mixer, but you got the beat BFO and a notch filter, which then you convert it, that converts it to audio, which is amplified. This is a volume control. Here's the audio and here's the output. That's the receive side. On the microphone side, the mic is amplified, goes through a potentiometer, which is your gain control for your microphone. It goes through a mixer. Here's the beat frequency oscillator here. Goes through this mixer, goes up here through a crystal filter, and then here's the transmit. And this is the what is a PTO? I wrote it down, I put it on a piece of paper, I don't have the paper. I used to know what that was, but anyway, this is a variable oscillator. That's where you do your tuning frequency. You turn in this, changes the frequency. Here's a crystal oscillator. They mix and they come out with your band pass filter here for a specific band, goes up here, mixes with the signal coming from here, goes up here, comes down here, it goes through this amplifier here, which has the ALC, which is the automatic level control that comes from the output over here. And here's the driver, and it's showing it going through the PA, which is the power amplifier. And then it comes out here, it goes out to the antenna. And that is as far. Oh yeah, John's going to get me. He's giving me 1 minute. That's sure better than last week where I went 20 minutes over.
I remember.
Here I was thinking it was 8 o'clock, and it was not. Anyway, we will get into this in much more detail next week. But folks, these are the radios, and these are the building blocks for radios. And you know, it doesn't really matter if you fully understand it. Just as long as if somebody's talking about it, you'll go, oh, Joe talked about that. I remember that. And for you that are getting your amateur extra, you'll need to study this a lot closer. But you'll get an idea on how most radios work. And there are some exceptions. But let's see what we've got here. Oh, this here's okay. Each one of you. I just got the 0 time left. Here are common circuit symbols. We will be learning what many of these symbols mean and how they apply to the radios that we're working with. But you who are going for the technician, read 3.2, components and units. Those going for the general, read 4.3, which is basic components. And for the extra, read 5.1. I hesitate having you read the first section of 5, because what they do is they go in and they tell you about all the chemistry of how it works from a chemical point of view for these transistors and diodes and that kind of stuff. Just read through it. Don't try to understand it. I know there's one more point I want to make. Those of you who are going for your general class license is it the end of June? Coming up here within a couple months. I think June 30th maybe is the very last day. That book is still good. But to be honest with you, they change very few questions. You could study this book and have no trouble getting a 98% on the test, because there's the likelihood of you getting what gets changed is not. But this license manual will no longer be valid after June 30th. And oops. Oh, and we've already been through the radio guts. So anyway, God bless everybody. Lord, thank you for helping us to learn. In Jesus' name, amen. Good night, everyone.
Good
Good night. Thanks,
night.
Joe.
Good night.
Great job.
Oh, thank you.
Good class today.
Oh, thanks.